Good morning to all of you. Welcome in new lecture of Math F242 Operation Research. Today we will start deterministic dynamic programming or simply dynamic programming. Audio video is okay?
Yes, sir.
So first, what is the dynamic programming? Dynamic programming determine the optimum solution of multivariable problem. Means with the help of dynamic programming, we can optimize multivariable problem in which we have more than one variable by decomposing it into number of stages, and that number of stages, and means in each stage we will consider only one variable. If we have the problem of n variables, then in the n stages we can decompose our problem, right? And in each stage we consider only the one variable. So what is the advantage in decomposing? Your solution hardness will reduce, right? And computationally it will become easier. So here, otherwise you have to apply the method with all the variables, which is little tedious. So a dynamic programming model is basically a recursive equation. So in general, dynamic is a recursive method. Dynamic programming is a recursive method, and in all the recursive method, always we have the some link with which all the recursion, all the iteration are linked. So here we assume that there is a one equation, right? We call it as a recursive equation linking the different stages of the problem in a manner that guarantee each stage optimal feasible solution is also optimal and feasible for the entire problem. Means, for example, you have started your solution from the stage 1. You have the n variable problem. You have decomposed your n variable problem into the n problem of one variable. Then you have solved the stage 1. So whatever the optimal and feasible solution of the stage 1, that will remain optimal and feasible for the stage 2. Then optimal and feasible solution of stage 1 and stage 2 will remain optimal and feasible for the stage 3, and so on. As you solve the as you compute the optimal solution of stage n, then that will be the optimal and feasible solution for the entire problem. That is the means nowhere the optimality and feasibility of previous stages will be disturbed. So although the recursive equation is common framework for formulating the dynamic programming, the solution details differ, right? So in all we have one common equation with which all the stages are linked, and depending over the problem, whether we are solving the problem of the queuing, whether we are solving the problem of the linear program or inventory or the reliability, accordingly solution technique will differ. But common is in all the common is that all the stages are linked by common equation, that is known as the recursive equation. Then recursive nature of computation in dynamic programming. So as I told you, we solve all the stages one by one, either from the first stage or from the last stage. So here we have the two type of the recursive method: forward recursive and the backward recursive. So what is the advantage of the recursive nature? Computation in dynamic programming are done recursively, so that optimum solution of one sub problem is used as input to the next sub problem. Means optimal and feasible solution of stage 1 will be the input for the stage 2, and with that, considering that, we compute the optimal solution of the stage 2. Then optimal and feasible solution for the stage 1 and stage 2 will become the input for the stage 3, and we compute the optimum solution of the stage 3. That's why the optimality and feasibility is not disturbing, because we are considering that optimality and feasibility input for the following stages. So at last we can solve the entire problem, and the optimal and feasible solution of the entire problem will be the optimal and feasible solution for the each stage. The manner in which the recursion computation are carried out depends on how the decompose the original problem. Right? So how you have decomposed the problem, depending over that, we have to opt the solution criteria. In particular, sub-problem are normally linked by the common constraint. So all the sub-problem means stage means sub-problem are linked by the common constraint. As we move from one sub-problem to next, the feasibility of this common constraint must be maintained. Means for each stage we have to modify the common constraint, because the common constraint link all the stage or all the sub problem. Let us take one uh, simple example. If you have to determine which one is the shortest route, if you want to start your journey from the starting point 1 and your destination is let's say point 7, and here we have the mileage, and in between we have the intermediate point, intermediate cities you can say, or intermediate location, and here we have the mileage. Now if you have to determine what is the shortest route, so how you can determine, what is the lemon technique? So as in the dynamic programming we have seen, we divide our problem into the stages. So what we have stage, how we are dividing our problem here. So first we divide from the start to first intermediate cities, then from the first intermediate cities to second intermediate cities, then from the second intermediate cities to the destination. So here we have the, right, let's say first node is the 0 1, then we have the first city is the 1, then we have the intermediate cities 2 3 and 4. So mileage are given to you. Here we have the 7 8 and 5. So naturally if you want to reach to city 2, then you have to travel 7 kilometers, because there is no other alternative. You have to travel 7 kilometers. For the city 3 you have to travel 8 kilometers. For the city 4 you have to travel 5 kilometers. Now you are in city 2, in city 2 and in city 2, and city 2 is linked to the city 5 only. City 3 is linked to the city 5 and 6. City 4 is also linked with the city 5 and city 6. So means for the city 2, feasible route is only one, that is of 12 kilometers. For the city 3, feasible routes are 2 of 8 and 9 kilometers respectively. For the city 4, feasible routes are again 2 for of the distance 7 and 13 kilometers, or 13 miles you can say. So what will be the, if you are in the intermediate city 2 and you want to reach city 5, so how many kilometers you have to cover? 7 plus 12, right? So here we have the, means for the city 2 to city 5 we have only the one route, so it will be the 12, right? From the city 3 to city 5 we have one route of 8 kilometer. From city 3 to city 6 we have one route of 9 kilometer. Then from the city 4 to city 5 and 6 we have the two alternatives, right? Or means one alternative 1 and 7. So here we have the optimal value Some mistake. Actually, I think some mistake here. Here we have means for this route he has to travel 7 plus 12. For this route he has to travel 8 plus 8, and for this he has to travel 5 plus 7. So minimum shortest route we have to determine. So he has to travel the 12 kilometer through the city 4. Similarly, here for the city 6, from the city 2 there is no feasible route. From the city 3 it will be the 8 plus 9, 8 plus 9, and from the city 4 it is 5 plus 13, 5 plus 13. So minimum is the 17. Minimum is 17. Now city 5 and city 6 are linked to the city 7. So optimal will be 12 plus 9, 12 plus 9, and here we have the 17 plus 6, minimum shortest route. So we have to take the minimum. So minimum is the 12 plus 9, 21, 17 plus 6, 23. So minimum is the 21. So what will be the route? 7. To reach the 7, optimal intermediate city is 5. For the optimal intermediate city is 12. So it is through 4, and then we have the 1. So this is the optimal, or you can say shortest route for reaching from node 1 to node 7. So here how we can write technically: shortest distance from node 1 to node 2, 7 miles. So we have only one alternative. So we have written directly from node 1. Shortest route, shortest distance from node 1 to node 3, 8 miles from node 1. Shortest distance from node 1 to node 4, it is a 5 miles from the node 1. Now shortest distance to node 5. Shortest distance to node 5. So what we have, we can be at the node 2, 3, 4. So minimum over the node 2, 3, 4. Shortest distance to node I plus distance from node I to node 5. So shortest distance to node I is 7 plus distance from node I to node 5, it is the 12. For the node 2, from the node 3 it is the 8, and then distance is the 8. For the node 4 it is 5, then plus 7. So it will come 19, 16 and 12. So minimum is 12, and that 12 is minimum from here. So that is from the node 4. Similarly, shortest distance to node 6. Shortest distance to node 6. So here, shortest distance to node I, that is the 2, 3, 4, plus distance from 2, 3, 4 to node 6. But you know that 2 is not feasible route. 2 is not feasible route. So here we take only for the node 3 and node 4. So it will become 8 plus 9 and 5 plus 13. So 17 plus 18. So minimum is 17, and that is coming from the node 3. Then shortest distance to node 7. So feasible route are from the node 5 and node 6. Then shortest distance to node I, that is the 12 and 17, plus distance from node 5 to node 7 and node 6 to node 7 are 9 and 6. So it will become the 21 and 23. So minimum is 21 through the node 5. So if you go backward, then you can determine the optimal route, optimal shortest route. The computation at each stage are the function of the feasible route. Means in each stage we have to check the feasibility, and that stage alone, and that feasibility you have to check in that stage only. The current stage is linked to the immediately preceding stage only without regard to earlier stages. Means if you are doing the calculation from here, so you have to take the data of this. You have to take the data of this. Only the 12 and 17. How the 12 and 17 are coming, that you have not to consider. Just you have to consider this data, right? Current data. You have not to consider what was in the intermediate city 2 or intermediate city 1. That you have not to consider. That is the main benefit here. So current stage is linked to the immediately preceding stage only without regard to earlier stages. We have not to bother about the earlier stages. The linkage is in the form the shortest distance summary that represent the output of the immediately preceding stage. Means here we just consider this 12 and this 17, right? Because already we have optimized here. So we will not take care what from where we have started and what are the intermediate steps. So in general, we write the problem in this form. Let fi xi be the shortest distance of node xi at stage I, because we have decomposed our problem into the three stages: stage 1, stage 2, stage 3, and define the distance between xi minus 1 to xi as a distance from node xi minus 1 to node xi. Then fi is computed. Fi we compute. Whatever we have done here, just I am writing in the refined form. So here we are determining the fi function value for the node 7 using the optimal value at node 5 and node 6. Using this concept only we are using, right? So the same I am writing here. So here then fi is computed from fi minus 1 using the following recursion equation. So what you have to write means function value for the node 7, it is the minimum of the shortest route for the from the all possible point, means 5 to 7, 6 to 7, of which function? Distance between 5 to 7, 6 to 7, plus what is the optimal value at node 5 and node 7. Clear? And for each I, for the stage 1, for the stage 2, for the stage 3, we have to write in this way. By chance, if you have to compute the for the second stage, means if you want to compute for the node 5. So for the node 5 means f2 bracket 5 is equal to minimum of the I is equal to 2, 3, 4. Because from the node 2, node 3, node 4. Then we have to take the distance from 2 to 5, 2 to 3 to 5, 4 to 5, plus optimal value at 2, at 4, at 2, at 3, at 4 respectively. And always we take f0 because it is a recursive formula. So always we have to initiate from particular value. So here we take the f0 as a 0. So here the xi is referred to as the state of the system at stage I. So this xi will termed as a state for the ith stage. State means what is the status of the constraint equation or limitation. What is the status of the limitation or linking equation? So state of the system at stage I is the information that links the stages together. Means state will give you will confine the complete information about the stages, so that optimal decision for the remaining stages can be made without re-examine how the decision for the previous stage are reached. Means for the future or for the following stages we have to bother, because it depends over the current optimal solution, and how the current solution is coming, that is immaterial for the following stage. The proper definition of the state allows us to consider each stage separately. So if you define explicitly the state, then that will discriminate the each stage easily and guarantee the solution is feasible for the all stages. And proper definition of the state guarantee the feasibility will not disturb in any stage. So what is the principle of optimality? Future decision for the remaining stage will constitute the optimal policy regardless of the policy adopted in the previous stage. Means for the optimality, we have to bother only the future stages. Whatever the past stages already you have computed, for that you have not to bother. So what I have told you, we have the two methods, either the forward recursion or the backward recursion. Forward recursion means we will proceed from node 1 to node 7, and in the backward we proceed from node 7 to node 1. So what the formula I have told you earlier, that is for the forward. In that we have gone from stage 1 to stage 7, or node 1 to node 7. But if you have to write the backward one, so for the backward one you have to proceed from the last node, for example from the node 7. So for that we have the formula: minimum of the all feasible route, distance between the xi to xi plus 1, plus optimal value of the fi plus 1. Again the I can take the three value 1 to 3, because we have the three stages. So the same question if you solve by the dynamic programming shortest route, so you have to make the table like this. So here where we want to reach, the nodes 5 and node 6 from the node 7. We want to reach through the connected roads to node 5 and node 7. Node 5 and node 6 from the node 7. So that from node 7 we write from here. So x4 denote we are at the node 7, and x3 is equal to 5 and 6 denote we want to reach to node 5 and node 6 through the feasible route. So what is the distance is given to you? If you recall the question, the distance between 5 to 7 and 7 to 6 to, right? So here we have the distance from 5 to 7, 9, and from 6 to 7 it is 6 only. So here we write the 2. So 5 to 7 we have to go, 6 to 7 we have to go, and their distances are given to you 9 and 6. And we know that for the stage 3, because it is the first travel, so there is no previous calculation. So for the stage 3, the optimal distance will be the 9 and 6, and that optimal you have achieved from the node 7. That optimal you have achieved from the node 7. This is the node 7, from node 7 to node 5, and from node 7 to node 6. So it is given to you. So in this way we make the table. So here the optimal value for the state x4 in the stage 3 will be the from 7. Then if you want to reach x2, right? If you want to reach x2 from from X3 or from the node 5 and node 6. So in the stage 2, we have the following alternatives 2, 3, 4, and in stage 3, we have the alternative of the 5 and 6. So what is the formula? First, we take the distance between x2 and x3. First, we see the distance between x2 and x3 plus optimal value of the f3. So, optimal value of the f3 you have seen in the previous slide. So, optimal value of f3 is 9. Optimal value of f3 is 9, right? So, here it will be the, we have written here the optimal value 999, and the distance from 2 to 3, right? Stage 2 to stage 3, or you can say 2 to 5, 3 to 5, and 4 to 5. It is given to you 12, 8, 7. So that will be the total distance covered from the node 7 to reach node 2, node 3, node 4. Similarly, for the city 6 or node 6, first of all, from the node 2 it is not connected, it means that is not a feasible route. And from the city 3 and city 4, city 6 or node 6 is connected, so their distance are mentioned here. It is a 9 and 13. So for the previous, from the previous iteration, the optimal value for the 6 is the 6 only. So 9 plus 6, 13 plus 6, so it will give the 15 plus 19. So what is the minimum? 21. What is the minimum between the 17 and 15? 15. What is the minimum of the 16 and 19? That is the 16. This 16 is coming from here. That's why I have written the x2 is equal to 5. This 15 is giving here the 15. So that is from the node 6. This 21 you are getting from the this. So that is the from the node 5. So that is the optimal value for the x3. Similarly, for the state variable x1, means when we are at the node 1. When we are at the node 1, we can reach the node 1 in backward through the city 2, city 3, and city 4. So what is the optimal of the city 2? Optimal of the city 2 is given to you as a 21, and what is the distance between the 1 and 2? It is the 7. So it will become 21 plus 7 is equal to 28. Similarly, for the x2 is equal to 3. So when x2 is equal to 3, optimal route is the through the 6. Optimal route is through 6. So total distance will become because optimal for the city 2 is given to you, optimal it is given to you as a 15. So 8 plus 15, so it is the total 23. Similarly for the city 2, so it is the optimal value from the previous table. We see it is 16, and current distance, that is a 5, so it is 21. So when it is 21, that is the minimum. So that 21 you are getting from the x2 is equal to 4. x2 is equal to 4. So in this case, we can get the answer, right, when the here we have the 1, then 4, right, then 4, and here the minimum is, in this case minimum is the 15. So it is through 6 and 6 to 7. That is the feasible route 1, 4, 6, 7. Let us have this example. Any doubt in this part? Till now, proper dynamic I have not started. Just I am giving you the idea about the stage and state. I am an avid hiker. Last summer, I went with my friends G Dawn on 5-day hike and camp trip in the beautiful White Mountains in New Hampshire. We decide to limit our hiking to an area comprising three well-known peaks: Mount Washington, Jefferson, and Mount Adams. Mount Washington has 6-mile base peak trail and corresponding base peak trail for the Mount Jefferson and Adam are 4 to 5, 4 and 5 respectively. So what is given to you? Let us suppose we have this figure. So here the distance from base to top, it is 6 mile. Similarly, for the Jefferson, distance from 6 to top, it is 4 mile, and for the Adam, it is 5 miles only. Right? It is 5 miles only. Now, the trail joining the bases of the three mountains are 3 miles between Mount Washington and Jefferson. It is given to you from where you are starting, right? So the distance between Mount Washington and Mount Jefferson is given to you 3, and Mount Washington and Mount Adam is given to you as a 5, and the distance between Mount Adam and Mount Jefferson is given to you 2. So here it is written, the trail joining the bases of the three mountains are 3 miles respectively to Mount Washington and Mount Jefferson, 2 miles between Mount Jefferson and Adam, 5 miles between Mount Adam and the Washington. So we stated on the first day at the base Mount Washington and return to the same spot at the end of 5 days. Something we started the first day at the base of the Mount Washington and returned to the same spot at the end of the 5 days. Means here we start on the day 1 from here, and after roaming or after the 5 days again we are at this point. Our goal is to hike as many miles as we could. So here we want to maximize the total distance covered. In 5 days, they want to maximize total distance cover. We also decide to climb exactly one mountain each day. So that is a restriction. On each day, they can travel only one mountain. And to camp at the base of the mountain, we would climbing on the next day. Means on the day first, you have to go up and then you have to come down, right? Then you have on the next day either you can visit Jefferson or the Adam. So at the base of that mountain you have to stay at night. So on the day 1, how many kilometers they will cover? 6 up plus 6 down plus 3 for the Jefferson, 6 up plus 6 down plus 5 for the Adams. Right? That is the total distance covered on the day first. Additionally, we decide that same mountain could not be visited in any 2 consecutive days. Means there is a restriction on the same mountain we cannot repeat. How did we schedule the hike? So here we have to schedule the hike, means on the first day which mountain, on the second day which mountain, on the third day which mountain. so that total distance cover in 5 days will be the maximum. So here, first,
Sir,
yes,
sir, can you
yes.
explain that how you calculated number of miles covered in day one?
For example, on the day one, it is given to you. You have to start from the Washington base. So six up, right? Six up, then six down, six down, and on the second day, if he want to travel the Jefferson, so base distance is 3. So 3 for the 3 for the Jefferson and plus 5 for the Adam. So total distance will become the 15, and here here the total distance will become the 17 for the day first. Clear?
Yes, sir.
So uh, here I will show you that thing. Define the node Ni. We define the node Ni as N denote any mountain, WJA for Washington, Jefferson, and Adam, and I denote on which day we are visiting. So on the day first, we have to visit the Washington, so W1. On the second day, we have the choice of Jefferson or the Adam. If on the second day you are at the Jefferson, so on the third day you can visit either the Washington or the Adam. If you are on the second day, if you are at Adam, then on the third day you have the choice. You can visit either the Washington or the right or the Jefferson. Clear this part? On the third day, if you have visited the Washington, if on the third day if you visited the Washington, then you have the choice to visit either the Jefferson or the Adam on the fourth day. If you are if you have visited the Jefferson on the third day, then you have the choice of you have the choice of Washington and the Adam for the fourth day. If you have visited Adams, right? Adams on the third day, then you have the choice to visit the Washington and the Jefferson on the fourth day. Thus, with the same logic means W4, J4, and A4 to J5 and A5. Then at the evening of the fifth day, we are at the base of the Washington. We are at the base of the Washington, so that we are writing the as a W6. So on the first day you have visited the W1. On the next day you can visit either the Jefferson or the Adam. So total mileage will be the 15 plus 15 or 17. So this 15, how you are getting the 15? 6 plus 6 plus 3, and how you are getting this 17? That is the 6 plus 6 plus 5. Then on the second day, if you are on the you are visiting the Jefferson. So Jefferson means 4 up, 4 down. Then either you go to Washington or you go to the Adam, right? So it is the 4 plus 4, then to the Washington 3, and to the Adam it is 2. So it can be the 4 plus 4 8 plus 3 11 or 10. So it is the if you are on the right, if you are at the node J3, if you are at the node J3, so it is either 11 or 10, right, or 10. If on the second day, you are they are on at the mountain Adam, so here they will travel 5 up, 5 down, then either the Jefferson or the Washington. So it is the 5 up, 5 down, 2 to the Jefferson, and 5 for the Washington. So 5 plus 5 10 plus 2 12, and 5 plus 5 10 plus 5 15. So here we have the either the 15 or it is the 12. So in this way we can draw the network, right? The same the same whatever we have done previous question for the shortest route. Now we will go for the longest route. Any doubt in making this diagram? So from
Excuse
the
me, sir.
stage,
Sir, was it
yes,
given in the start that we start with Washington, or can we assume anything?
it is given, it is given in the question.
Okay,
ये यहाँ पे लिखा है, this is given,
okay, sir.
and it is also written कि on the last day we have to reach there only. ठीक है ना? That's why we have taken the Washington at last. Any other doubt? And there is a restriction, not on consecutive day you can visit the same mountain. So now we are solving this question by the forward recursion. So forward recursion means on what is the stage one? Stage one, in the stage one we have to go to the base of Jefferson or the Adam. So that is the J2 and A2 from from W1. So longest distance is we have only the two routes. So 15 and 17. So here we have computed the from the Washington on the day one. For the stage two, right? For the stage two, we have break the our problem into the stages, right? Stages. We have decomposed our problem into the stages, right? Means W1 J2, W1 A2 stage 1, then J2 W3, J2 A3, then A2 W3, and A2 J3. That is the another stage. So now for the stage 2, we have to reach to W3, J3, and A3. What are the feasible route? Either through, right, means W3. So either through the J2 or A2, J2 or A2. And because in the previous stage we are at the either the J2 or A2. For the J3 only you are at the A2. For the A3 you are at the J2. We have only one feasible route. So here we have the longest distance. So longest distance will become maximum of 15 plus 11, 17 plus 15, that is the 32. So this 32 you are getting from the A2, right? This 32 you are getting from the A2. Then J3, 17 plus A2, that is the 29, again from the A2. And for the A3, the longest distance will be the 15 plus 10, that is the from the 25. 25, that is from the J2. Similarly, for the stage 3, in the stage 3, we will reach to Washington 4, Jefferson 4, Adam 4, from the Washington 3, Jefferson 3, Adam 3, or with feasible route. So it will be the maximum of for the W4. For the W4 we have to check for the W4 we have to check for the J3 and A3. For the J4 we have to check from the W3 and A3. For the A4 we have to check for the W we have to check for the W3 and J3. So that is written here. So maximum of 29 plus 11, 25 plus 15. So maximum will come from 29 plus 11, that is the 40. Then maximum of 32 plus 15, 25 plus 12. So it is the 17. Then maximum of 32 plus 17 and 29 plus 10. So all the maximum we have underlined here. So maximum value will be the 40, 47 and 49. This 40 you are getting because both will give the 40. So here you are getting the optimal value from the J3 and A3. Similarly, this 47 you are getting only from the W3. So here we have written from the W3, and this 49 you are getting from the W3. So here we have the optimal route for the W3. Similarly, in the stage 4, we reach to stage J5 and A5 from from uh, W4, Jefferson 4, Adam 4. For the J5, we have only the W4 and A4, and for the A5 we have only the W4 and J4. So maximum of 40 plus 15, 49 plus 12 means optimal value of previous stage plus current distance. Optimal value of previous stage plus current distance. So it will come 61, 61 from the A4. Similarly, maximum of the 40 plus 17, 47 plus 10, that is the 57, and that is from the W4 or J4. Then W6, so W6 from W5, not J5, from J5 and A5, from J5 and A5. So maximum of the for the J5 we have seen maximum is what, 16. For the A5 maximum is what, 57. So 16 plus 11 means optimal value plus current distance, optimal value plus current distance. So it is the 72. So 72 you are getting from the both. So that's why here we are writing the from J5 to J5 or A5. So it means total maximum distance you can cover in 5 days will be the 72 miles. Now, which route it should follow? So for that, we start from the stage 5. So for the W6, optimal location is the J5 and A5. So for the W6, optimal location is J5 and A5. And for the J5, optimal is A4, but for the A5, optimal is W4 or the J4. So here for the J5, optimal is only A4, but for the A5, optimal is J4 or the W4. Then for the W4, optimal is either J3 or A3. For the J4, only W3, and for the A4, only W3. So here we have written for the A4 only W3, for the J4 only W3, but for the W4 either A3 or J3, either A3 or J3. Then for the W3, optimal is A2, for the J3 optimal is A2, and for the A3 optimal is A2. So on the second day, optimal is A2, optimal is A2. Achha, for the A3, optimal is the J2, right? So here it is the J2, then A2, and on the day first we know that all are at the Washington 1, right? It means what will be the optimal, what are the alternative routes? On the day first you visit Washington, on the second day you visit Adam, then on the third day again you visit Washington, then Adam, then Jefferson. So we have the four alternatives, and all will give you the 72 kilometer. So in all route, you have to visit the Jefferson once and each Washington and Adam twice. So why it is so? Because for the Jefferson, this height, slant height is lesser than the 6 and 5. That's why it is happening like this. Clear? So the same thing, if you write in the technical way, right, in the technical manner, or whatever the way we solve in the exam, right? If you want to solve by the backward method or backward recursion, so for the backward recursion, the same thing we can write fi xi is equal to maximum over the feasible root, right? Feasible root means xi to xi plus 1, distance between the xi to xi plus 1 plus optimal value of the xi plus 1 fxi. Means now we are reaching from 6 to 1. So first we will solve the stage 1. So stage 1 means only in the stage 5 we reach to J5 and A5 from the W6. So we have only the distance. So it is the 11 and 15. So optimal is the 11 and 15 from the W6 and W6. It is 11 and 15 for the current optimal solution. So here we write the optimal solution, and the current optimal value from which variable. Uh, Similarly, stage 4. In the stage 4, you have to reach the city W4, J4, A4, either from the J5 or the A5. So here we haven't the feasible route. Here also we haven't the feasible route. So we take the maximum of D4x5 plus F5x5, right? So it will be the 15 plus 11, 17 plus 15. So 26, 32. So maximum is the 32. That 32 are getting from the A5. So that's why here we have written the A5. Then feasible route, this is not a feasible route. So only we have the one option, that is the 25. So when we write the 25, so it is through the A5. This is not a feasible route. So we have the only one option, that is the 23 from the Jefferson 5. So in this way, we proceed for the stage 3, then for the stage 2, then for the stage 1. So here also you can see you are getting the optimal mileage as a 72, and the same route you will get in the same. So you can solve any dynamic programming by the both approach, by the forward recursion or by the backward recursion. You will get the same answer. So more technical question I will do cover in next class. This is just introductory about the dynamic programming. Any doubt here?